So let's take a look at Newton's second law in two dimensions, and we'll also balance the forces in two dimensions as well to create equilibrium. So let's say we have two forces, one going down 5 newtons and one going towards the left. That's 8 newtons. So if we want to balance the forces in this scenario, we need to have a net force of 0. So if you look at this situation, if you think about it, how we can balance it, if there's two forces added to balance, we can have 8 newtons going towards the right to balance the left one, and we can have 5 newtons going up to balance the downward force. So let me draw those two forces, and that's how we can create an equilibrium situation in which all the forces are balanced. Which means that now we can look at the net forces in the horizontal and vertical directions. They're all going to be equal to 0. Let's take a look at an example with three forces and how we can balance the forces to create some equilibrium. So I have three forces, 10, 6, and 2. And my question is, how can we bring it to equilibrium? Equilibrium means net force has to be equal to 0. So if I have to balance it, I have to put all the horizontal and the vertical forces equal to 0. Which means that the left and right should be balanced, which is going to be balanced by 6 newtons going to the left. And the up and down forces can be balanced, but this is a little bit tricky because I have two forces already being applied on this object. So I'll have to add up those forces and then figure out what force will balance the added of the forces that I got, which will be 8 newtons going down. So that way I can balance two forces, 6 newtons to the left and 8 newtons down to balance it. Now there are other types of equations that you will see that there are two forces already applied, and my question is, how can I bring this to equilibrium? By adding only one force. So let's say take a look at how to balance it for the two forces. I need the opposite directions. When I draw those and add it, I need the green vector that needs to be calculated. So that's the one force, and the angle will tell me the direction of that one force. So if I use Pythagorean theorem to figure out the resultant vector, I got 10 newtons. Now about the direction, I can see it in the picture that it's partially going towards the right and partially going in the upward direction. So it's slightly at an angle. I'm going to use the tangent function, inverse function, and the opposite side is 8 in front of the angle, and the adjacent side is 6, so I got the angle of 53.1 degrees. So I can write my final answer as 10 newtons at 53.1 degrees. So let's take a look at another type of question that you will see in class. Let's say we have two unknown forces and I'm given only one type of force, and that force is also at an angle of 60 degrees. So my question is, what are F1 and F2 if this is an equilibrium? Now this will lead to another new concept or new idea of using components. And what do I mean by components? A component is how much a vector extends in a certain direction or a given direction. So what I mean by direction, I mean that how much it is in the horizontal direction and how much it is going to be in the vertical direction. So horizontal, I'm going to use X for horizontal direction and Y for vertical direction. And if I use those subscripts with the F3 vector, I can clearly see the one along the x-axis is going to be labeled as F3x, and along the y-axis is F3y. Now if I look at the picture, I can clearly see that F3x is balancing F1. So F3x and F1 must balance, and F3y must balance F2 in order to bring this object into equilibrium. So my next goal is going to be finding the components of the force that I already know, which is F3. So I'm going to use my SOHCAHTOA knowledge and apply those trig functions to figure out what is f3x and what is f3y. So f3x, I will have to use the cosine function, and the adjacent side is the f3x that I'm solving for. Similarly, for f3y, I'm going to use the opposite side, and that's the sine function, and solve it for the unknown side, f3y. So if I plug in the numbers in the calculator and solve it, I can get 30 cosine of 60 is 15. For f3y, I will get the y component as 25.9. Now I've figured out f3x and f3y, but I haven't answered the question yet. So what it is going to tell me that the magnitude is the same, but it's going to be in the opposite direction to f3x. So I'm going to plug in the value or the answer for f3y for f2, but I'm going to also explain the direction along the f2 vector. Now let's take a look at another type of question where I have a normal force and a gravitational force making an angle of 90 degrees. I also have the object tied to a rope which is going to be pulled with a certain force. Let's say it's 12 newtons. Now I already know that equilibrium means net force is equal to 0, which means that the forces are balanced in each direction. And what I mean by each direction, I mean that I'm going to look at the x and the y direction. And if I break down the tension force into its components, I have Ftx and Fty. Now if I look at the angles of this triangle, Ftx is actually going to be my opposite side of in this triangle. But I also see that the normal force is going to be balanced by the x component, and the gravitational force is balanced by the y component of the tension force. So I'm going to use the right trig functions and solve for the x and y components of the tension force. And that will give me 6 newtons for the x component, and solving for the y component, I can rearrange the equation again and solve for Fty, and it will give me the answer of 10.4 newtons. Now if you notice that gravitational force is in the downward direction and it's balanced by Fty, so I'm going to write it down as 10.4 newtons down, whereas the normal force is towards the right, so I'm going to write it as towards the right. These are not balanced, and that's the scenario that we have not seen in this video yet, but we have seen it for Newton's second law, that if it's not balanced, it's not in equilibrium, which means that the net force is not equal to 0, and that's where we can use Newton's second law, which is net force is equal to mass times acceleration. But what we have to do in 2 dimensions is going to be slightly different. What we have to do is we have to break it down or split it up into 2 parts. One is along the horizontal direction and the other one is along the vertical direction. So let's do an example to help us understand this. So let's say we have 20 newtons to the right and 40 newtons going down, and I have a F3 force, and this force that is being applied is causing an acceleration of 2 meters per second squared towards the left on a mass of 5 kilograms. So when I draw these components of the F3 vector, I can see one is along the x component, x direction, or the direction of acceleration. So I'm going to figure out the net force in the x direction by adding the forces 20 and F3x and using Newton's second law, because I know the acceleration in that direction is -2 because it's going towards the left. So I solve for the x component, but I still haven't figured out the y component. If I look at the diagram, the y component is actually going to be balanced exactly with the 40 newtons going down. So that's what I need for the F3y as 40 newtons, but it's going to be pointing in the upward direction. So when I draw that vector and put them together as with head to tail rule, I see the blue vector is going to give me the resultant force F3. So I'm going to use Pythagorean theorem, and I'm also going to use the inverse tangent function to figure out the angle, and I can find F3 as 50 newtons at 53.1 degrees.